and welcome to NPTEL MOOC on arbitrary electromagnetics for engineers. In this module we will continue the study of uniform plane waves. In the previous module we have seen that Ex component of the electric field, and we assume only Ex component for moment, that exhibits a dependence on Z and T, where we have assumed Z to be the direction of the propagation of a wave. Then it satisfies an equation that is very similar to the equation satisfied by the voltage wave on a transmission line. Okay. That equation is the one dimensional wave equation, where one dimension refers to the fact that the voltage is propagating along the Z axis, and therefore it is a function only of Z coordinate. Of course, it is a function of time coordinate because we want to allow for any general time variation. While we were discussing in the last module, we also said that we can assume in general, or we can specify in a particular case, in fact not general, in a particular case we can specify that the electric fields or the waves associated with the electric fields are sinusoidal type of a wave of frequency omega, propagating along the Z axis with a propagation constant of beta, and we are of course assuming that there are no losses in the medium, and therefore the question of attenuation as of now has not arisen. Okay. So, we have only looked at media which is uniform, isotropic, lossless, homogeneous media. Okay. So, for this media waves are assumed to be, or waves are lossless, and they are propagating in as a sinusoidal waves along Z and varying with respect to time with a frequency of f hertz. Okay. The corresponding expression for that is given by this Ex of Zt is along this expression, where up, the phase velocity, is given by omega by beta, and we know that beta is equal to omega by up. I mean, I am just inverting this relationship a little bit, and I know that phase velocity up for the free space media which contained, or for the media which had the medium constants of mu and epsilon, then this beta was equal to omega into square root of mu epsilon. And the phase velocity up, which is 1 by square root mu epsilon for the vacuum. Okay. So, this for the case of a vacuum becomes 1 by square root mu naught epsilon naught, and if you plug in the values of mu naught and epsilon naught into this expression, this turns out to be 3 into 10 to the power 8 meter per second, approximately. This is 3 into 10 to the power 8 meter per second. So, in free space, in vacuum, a wave would propagate as a light wave. So, light is an electromagnetic wave because it does propagate at a same velocity as a light wave. So, this was in fact the argument that Maxwell used. Maxwell found the values of mu naught and epsilon naught, and then calculated the velocity factor or the velocity value, and then showed that that was equal to the speed of light. And once that took off, then people started recognizing that it's light is an electromagnetic wave at a different frequency, just as a microwave signal is a light at a different frequency. The frequency of a microwave is very low, whereas frequency of light is very high. So, apart from that distinction in terms of the frequency, they are all electromagnetic waves. Okay. What about the H component? We have shown that only Ex, I mean we have written only the Ex component, but I should be able to find the corresponding magnetic field component, and I can find that by appealing to this equation. Del cross E is equal to minus mu del H by del T, and because we are considering the Cartesian coordinate system, writing this del cross E is very easy. It is easy as a pie. So, this is x hat, y hat and z hat. What component do we have? Well, I need to first write this as del by del x, del by del y and del by del z. What component of electric field we have? Only the Ex component. Ey and Ez components are 0. So, when you take the determinant of this one, you will immediately see that there cannot be any x component, this will be 0. There cannot be any z component as well, because del by del x times 0 is 0 minus del Ex by del y, and Ex is not a function of y, Ex is a function only of z component. Therefore, what component of this one we will have? We will have only the y component. Okay. And what would be the y component given by? Del Ex by del z, and this should be equal to minus mu del H by del T, which therefore implies that H will be equal to, so this is the y component that I am looking at, therefore there will be a minus sign to this one. So, this minus sign and this minus sign cancels with respect to each other, and clearly because electric field is only along the y component, the curl of electric field is along the y direction, the magnetic field must also be in the y direction itself, because that is equal to h, or rather time derivative of h. So, I have mu del h. So, instead of writing this del h in a vector form, I would like to write this as del hy by del t. This will be equal to del Ex by del z, but I know already what is Ex. Ex is E0 cos omega t minus beta x. So, if I differentiate this E with respect to z, I will be pulling out minus beta from this. So, I obtain minus beta E0, and then I have this, instead of cosine I will now have a sine omega t minus beta z. Okay. This will be equal to mu del hy by del t, but now integrating on both sides with respect to time, what do I obtain? This would be mu, and integration with respect to time will take this away. So, I will have hy, and to the right hand side we will have minus beta E0, and what is the integration of sine with respect to time will give you? This will give you minus cos, right. So, this will give you minus cos, and there will be a division by omega, correct, because it is sine omega t with respect to dt that you are going to do. So, when you do that one, this becomes cos omega t minus beta into z. So, therefore, hy can be rewritten by putting this mu down here and writing this as beta by mu epsilon times E0, and if I call beta by mu epsilon, okay, times E0 as h0, which is the amplitude of the magnetic field, what will be this beta by omega mu? Beta, as we have already seen from the above, is given by omega square root mu epsilon. So, dividing this one by omega will cancel omega on both sides. So, I obtain square root of, substituting this omega square root mu epsilon for beta, what I obtain is square root of epsilon by mu. Okay. But I have already told you that E0 by, or rather I told you that h0 is given by E0 by eta, okay, in the previous module. So, I can define eta as the impedance, okay, I can define eta as the impedance as the ratio of electric field amplitude to the magnetic field amplitude, and that is equal to 1 by square root of epsilon by mu, alternatively this is equal to square root of mu by epsilon. Okay. This is very similar to the transmission line characteristic impedance. In the case of a transmission line characteristic impedance, you had square root of L by C. In this case, you have square root of mu by epsilon. The characteristic impedance of a transmission line was the ratio of a positive travelling voltage to the positive travelling current. In this case, the characteristic impedance is the ratio of the electric field amplitude to the magnetic field amplitude, and the electric field will be along the x direction, magnetic field is along the y direction. So, that is the key difference that you have to see between the two. I will leave this as an exercise to you, okay, or you can try. If I assume instead of Ex component, if I assume Ey of z comma t as some constant Ey naught cos omega t minus beta z, okay, then you can show that it is the Hx component that will be important, and the ratio of Ey to minus Hx will be exactly equal to square root of mu by epsilon. Okay. So far so good. Why is this called a plane wave, right? If you look at the electric field E and assume only that there is Ex component, Ey component is assumed to be 0. This Ex component, if you look at, or if you try to find what is del dot E, right, can you see what will happen to del dot E? This will be equal to 0 because Ex will be function only of z and this one. So, if I consider the case where z is equal to some constant, and I can consider z equal to 0 as a constant, and if I plot at a given value of time, if I plot the electric field component, so I know that Ex of z and t is given by Ex naught or some E0 constant or cos of omega t minus beta z, right. So, this is what my Ex of z and t is. If I consider the z equal to 0 plane, which is a constant plane in the space that I am considering, and I also freeze time t to a particular value. So, let us say t is equal to 0 in this case, okay, and it can be anything. So, for any value of t, if I fix the value of t, And if I now look at what would be the direction of the electric field and what would be the strength of the electric field in this plane z equal to 0, I see that the electric field will be directed along x axis. This is the direction of the x axis that I am considering, and the strength of this electric field will be completely independent along the x axis itself. Okay. So, it does not matter where I am standing, the strength of the field at x equal to 1 it will be the same, at x equal to 2 it will be the same, at y equal to 1 it will be same, y equal to 2 it will be same. So, it will essentially be completely independent, and if you look at how these amplitudes are all present, they will all be in the form of a plane. Okay. So, this is the plane wave that we are talking about. Now, that is not the complete story, this is what we called as the constant amplitude. So, if I collect all the constant amplitudes, okay, at many different times, these constant amplitudes will always form a plane. Okay, it is like a flat surface kind of a thing, but that is not the full story, because we also need to talk of the phase front. What is the phase front? It is the collection of all points, okay, all electric fields which have the common phase. Okay. And when you see that if I have to have a common phase, I need to maintain both omega t and omega t and beta z in such a way that omega t minus beta z must be equal to some constant, and whenever I consider that particular for example, I consider the phase fronts for pi by 2, in which case omega t minus beta z must be equal to pi by 2. So, I for example fix my z, and then I find at all different times where this condition is satisfied, and when I look at that condition, what will happen, or when I consider that particular thing, then the phase constant, okay, implies that the phase front will also be a form of a plane. Okay. So, that is the reason why we call this as a uniform plane wave. Okay. In contrast to that, suppose I have a source here, and then the wave is generated from this source, and it is in the form of a cylinder. So, it is expanding in the form of a cylinder, or you can think of a wave coming from an explosion where it would be moving in the form of a spherical cloud. So, in this case, although if you consider a constant so if you consider the constant amplitude and the constant phase, those constant amplitudes will always be forming a surface which is sphere, and sphere is not a plane. So, spherical waves as what we call them, or cylindrical waves as we call them, are distinguished by the way their amplitude fronts and the phase fronts are distributed. Okay. So, that is the difference between a plane wave and non-plane wave. We will for now, and in most of the cases in courses, in most of the lectures in this course, we will be considering only the plane waves. Okay. We have seen one type of a wave in which the direction of the wave was always along the z axis. What if I want to specify a wave in an arbitrary direction? Okay. So, I want to now specify a wave which is propagating along, let us say this direction. Okay. So, I will consider this as x and z, and appropriately this as y. So, I do not know, this should be minus y, or so x cross y, this is okay. So, we can consider this as the y axis. So, let me say I want to talk about a wave which is propagating in the x and z plane and making an angle of theta with respect to z axis and an angle of 90 minus theta with respect to the x axis. How do I describe this wave? Can I still have a plane wave? Yes, you will have a plane wave where the wave is propagating along this direction. Okay. So, what should happen to my electric field and magnetic field? Well, when the wave is propagating in the xz plane, I know that if I still want to claim a TEM wave, electric field must be perpendicular to the direction of propagation, and this electric field must be perpendicular to the direction of propagation. Again, you have two choices, right. So, you have one choice which is shown here, or you can have a choice which would go like this. If I fix electric field to be perpendicular and lying in the same plane, then the magnetic field must be perpendicular to both of these, and it should be in such a way that E cross H must point in the direction of propagation. So, if this is my electric field, then the magnetic field must be perpendicular. So, let me erase this Y field. So, if I show that in the two dimensional case I am looking at, if my electric field is lying in the plane, right, then the magnetic field must in this case lie along Y axis. So, that this E cross Y should be showing you the direction of the propagation which is along the XZ plane. Okay. So, this is one solution for me, or I can have an electric field perpendicular, that is along the Y axis. So, that electric field times h will now be in this particular loop, I mean in this particular plane, x and z plane, and y cross that h must show you the direction of the propagation, okay, as demanded by the TEM condition. Okay. So it is possible for us to specify waves propagating an arbitrary direction. Before I can show you that, I need to introduce you to the phasor notation or the complex notation. Okay. You know already this, if V of zt is given by V0 cos omega t minus beta z, we said that if you want to obtain the corresponding phasor, you first convert this cos omega t minus beta z into e to the power j omega t minus beta z, okay, times V0. This is the complex notation. Okay. This is not the phasor, this is just the complex notation where electric field is in the form of e to the power j, I mean voltage is in the form of e power j omega t. To go to the phasor domain, I need to drop this factor e power j omega t so as to obtain V0 e power minus j beta z. I can rewrite this e power minus j beta z as e power minus j z hat beta dot z z hat, where z is the length or the direction, z is the coordinate value and z hat is the unit vector along the z axis. This I can consider it to be a vector itself, right. I can consider this to be the propagation vector, and this propagation vector in this case will be directed along z axis. So I can rewrite this exponential phase factor as e power minus j beta dot r, where r is the position vector. So if this is the z axis, from the origin the r vector is given by x hat plus y hat plus z hat, right. So let me go back to the 3-dimensional case. This is x, this is y and this is z. The position vector at any point, along this one or at any point can be written as, from the origin, what is x hat plus y hat plus z hat. If I consider the wave propagating only along the z axis, then what will happen to the phase factor? It would be e power minus j beta dot r. This is the direction for beta, this is the position vector r, and beta dot r will be the dot product between this propagation vector and any point or the position vector, right, and that would be just the projection of this r onto the z axis, okay, and that is precisely what this beta dot r is telling you, right. If the wave is propagating along z axis, then e to the power minus j beta dot r is a fancy way of saying e power minus j beta z. But the situation is different when I consider propagation in an arbitrary direction. So I said that we will have an x z plane and I am considering propagation of the wave in the x and z plane, correct, and this is making an angle of some theta with respect to z. If this is the propagation vector beta having the magnitude beta, then this propagation vector beta can be rewritten as beta x hat plus beta z hat, correct, and I can find out what is beta x. Beta x is nothing but propagation constant beta times sin theta, whereas beta z is equal to beta times cos theta. Okay. Once I have this, what will happen to the phase factor? The phase factor becomes e power minus j beta dot r. Okay. So beta is beta sin theta, beta cos theta along the x and z components. The position vector r is x hat plus y hat and z hat. Therefore, this becomes e power minus j beta x plus beta z. Okay. So you see that the direction of propagation is along plane in which the propagation vector has two components, beta x and beta z, and if I now assume that the electric field is perpendicular to this and lies in the same direction, I can show that electric field also has two components. One component will be along the z axis and the other component will be along the x axis. Okay. I can find out what those components are, but right now that is not the point. For example, if I give you a wave propagating in the xz plane at say 45 degrees with respect to the z axis and having a magnitude of the propagation constant of 2 radians per meter, what will be the component for beta x? Beta x will be 2 cos 45 degrees, beta y or beta z will be equal to 2 sin 45. But beta x will be equal to 2 into root 2, this would also be 2 into root 2, cos 45 is 1 by root 2, so this is 2 into 1 by root 2. Okay. So you can find this. So this is, you can still have a TEM condition, but the wave is propagating as a TEM wave, but it is propagating in a arbitrary direction. Okay, there is no reason why you should stop only with two dimensional plane kind of a propagation, in the sense that beta can have only beta x and beta z. You can actually have beta propagating in any direction. So you will have beta x, beta y and beta z. The condition for a TEM wave is that electric field must be found which is perpendicular to this beta vector, and the magnetic field must be found which is further perpendicular to the 2. Before we close this module, I would like to actually show you the relationship between E, H and beta in a slightly different manner, okay, which will allow you to find out H given electric field and the propagation vector beta. Okay. We start with del cross E is equal to minus del B by del T. Now here, because I was considering the phasor notation by dropping the time dependence, and I will do the same thing for the magnetic field vector B. So if I express everything in terms of a phasor, and this is how I express the phasor in the vector, or I express the vector phasor, I put a small tilde on top of it. So for the phasor there is no time dependence, because that is precisely what the definition of a phasor is, and instead del by del T becomes J times omega, where we will assume that this B field, original B field, is of form cos omega t minus beta into z, okay, or rather cos omega t minus beta dot r. Okay. So del by del T will be replaced by minus j omega. I can do the same thing for the magnetic field. Magnetic field will be equal to j omega epsilon times electric field. Okay. This j omega b can be rewritten as j omega b can be written as minus j omega mu into h, because b is equal to mu into h in the phasor notation as well. Okay. Now what is the assumed phasor for E? This was some constant E0, which is the vector constant E0 telling you the direction of the electric field, times e power minus j beta dot r. This is what we have assumed. This E0 is a constant vector, right. So if I consider del cross E, right, this will be equal to del cross E0 e power minus j beta dot r. So now I am looking at one scalar multiplying a vector, and then I am taking the curl of this entire thing. So I am looking at a scalar f times the vector a. So what is the curl of f a? So if I remember it correctly, the corresponding identity for a vector will be f del cross a, okay, plus a times gradient of f. So will that give me the correct answer, or a cross gradient of f? So this one will be a vector, which is okay. Gradient of f will be a vector, but then I have a vector to multiply. So in this case we have a vector identity which is given by this one. So del cross f a is equal to f del cross a plus a cross del f, and identifying a with E0 constant vector and f with the phase factor e power minus j beta dot r, this fellow will be equal to 0, because curl of a constant will be equal to 0, and you can show that gradient of f simply pulls out this minus j beta vector out of it, okay, and of course it will still be e power minus j beta dot r, that you can write in the same way, and a was E0. So I can go back and substitute for a, which is E0 in this case, cross minus j beta, this is a vector, it will still be associated with this phase factor e power minus j beta dot r, that let us write. This should then be equal to, from the first equation, minus j omega mu h phasor. Okay. Now minus j on both sides will cancel, and h phasor can therefore be written as E0 cross beta. So I have E h beta. So this should actually have been del gradient of f cross a. Okay. So there has to be a minus sign over here you can put. So this would be a plus somewhere, or gradient of f will be a minus. So this has to be a minus sign somewhere, and therefore beta should come on this side and E0 should go on the other side. Okay. So I have E0 vector cross whatever that beta that I had, right. So beta was the vector beta itself divided by omega mu. I am assuming that e to the power minus j beta dot r is the same for both sides. So, I am removing that e power minus j beta dot r phasor on that. So, what I get is e 0 cross beta by omega mu. So, this is the phasor for the H without the phase factor that I can put in, but I can write beta as a vector, a unit vector along beta multiplied by the magnitude of the vector beta itself. Substitute that into this expression to show you that H is equal to, this is beta cross E0. So, this is to be beta 0 cross E, sorry, beta cross E0, okay. And then you can substitute for beta as the vector unit vector beta hat times beta in this one, and then show that the magnetic field H will be given by beta by omega mu the vector beta hat cross E0, and this beta by omega mu we have already shown it to be equal to 1 by eta. Therefore, the phasor H can be computed without really worrying about that. So, you will have beta cross E0 divided by eta. So, this equation, okay, allows you to calculate the magnetic field provided someone tells you the component or the vector propagation vector beta as well as tells you the direction of the electric field. Okay. I request you to verify this equation again by the help of the vector identities and try to solve this one for the previous example for the arbitrary directed electric field that we considered. Thank you very much.